Thank you very much and for the introduction. And it's a great honor for me to be here to share some of our recent study. So the first topic I would like to share with you guys is on the value of orderly electric vehicle charging in carbon emission reduction. Okay, so this figure actually shows the surface, the air temperature, the anomalies in 2024. Why I present this figure here at the very beginning? Because 2024 is the first year to exceed 1.5 degrees Celsius above pre-industrial level. So I'm just wondering how many of you guys have a sense, regarding the 1.5 degrees Celsius. Okay, this number is quite special, okay, because this is exactly the goal we would like to control, okay, under the Paris Agreement. It means what? It means that actually we already failed to achieve the goal, okay? So this is pretty bad. Then the government need to do more, okay, to control the temperature increment. So the transport sector was responsible for 25% of global greenhouse gas emissions since 2010. 25% is not a small number, right? Then we are going to imagine, hey, what if we can reduce the greenhouse gas emission from the transport sector? Then actually it's very likely to help us to reduce the temperature, okay? Or at least to mitigate the impact. So, and furthermore, it's reported that electric vehicles may reduce the greenhouse gas emission contributed by the transport sector by 50% to 60% in the Europe, and by approximately the 40% globally, okay? So if we multiply the 25% with 40%, then it means that, hey, if we promote the electric vehicles, then it's very likely that we can reduce the greenhouse gas emission by 10%. Ideally, right? And I arrived here yesterday and I can see lots of electric vehicles in this city as well. So this is an old picture, okay, to show that how different governments, they would like to phase out the gasoline vehicle and to adopt the electric vehicle or zero the emission vehicle, okay? And in China and in Shanghai, this figure shows you some data. Yesterday, Professor Inhit mentioned that, hey, the local government would like to set a goal to increase the electric vehicle sales to be more than 50%, okay? And actually, in Shanghai, we already achieved this goal in 2024, okay? So the new sales, the penetration rate is 58%, okay? And for the whole country, it's close to 50%. So, why it's a good signal to see the high penetration rate of electric vehicles in our daily life, but the amount of carbon emission reduction yielded by electric vehicles heavily depends on their charging schedules, okay? It means what? Without controlling or without regulating the electric vehicle users' charging behavior, actually we may not achieve, okay, a very good carbon reduction. So this figure shows you one example, okay? So when the electric vehicle is operating on the road, it emits zero carbon emission, right? However, when the electricity is generated, it needs the energy, right? And if the energy is to generate 1 kilowatt hour, electricity comes from the green energy, green resource, for example, the wind power or the solar power, okay? The carbon emission is only 5 to 15 grams, okay? However, if the electricity comes from the polluted resource, for example, like coal, then unfortunately the carbon emission is going to be as high as 1,000 grams. So there is a saying, okay, if we don't control the electric vehicle users' charging behavior, actually its carbon emission is even higher than a gasoline vehicle, okay? So to be honest, I'm just curious though, yeah, but I would like to validate whether this is true or not, okay? That's one of the first questions I would like to answer. And secondly, what if we can control the charging behavior of the electric vehicles, then what's the maximum the carbon reduction we can achieve, okay? So this is the second question we would like to answer, or the main question we are going to answer. What's the maximum amount of carbon emission that can be reduced by electric vehicles when they behave properly? Or here we define it as orderly charging behavior, okay? You can treat this number as the potential, okay? The electric vehicle can reduce the carbon emission, okay? If it, for example, if it comes out that such an amount of carbon emission is actually pretty low, then maybe we can convince the government, hey, actually developing the electric vehicle may not help to reduce the greenhouse gas emission too much, okay? So we are not the first one to answer this type of question, okay? So for example, in 2020, since 2020, okay, we have a series of researchers investigate this question, okay? For example, some of them highlight that 30% carbon reduction through scheduled charging can be achieved, okay? While some others may highlight that only 1 to 10% energy saving, okay? So, however, most of these studies were conducted based on simple data survey or simulated profiles instead of real-world electric vehicle travel behavior. So this is going to be a big problem. For example, when we conduct a survey, okay, you just ask the people, okay, when you are going to recharge your electric vehicle, okay, from which time window to which time window and how much energy you would like to recharge. And that's it, okay? However, such an estimation may not be accurate, okay? It's quite biased. And secondly, it ignores the impact of charging behaviors on travelers' trip trends. What does it mean? It means that, for example, though in the survey I mentioned this one, okay? It could be the daily life, but in many situations, I may change my schedule. For example, tomorrow I would like to conduct a long trip. Then I'm going to change my charging plan tonight, okay? Secondly, they ignore the interaction between the EV charging behavior and the power plant operation, okay? It means that in the existing literature, the authors assume that, hey, the change of the charging behavior will not affect the operation of the power plant, okay? I mean, this could be true for New York City, okay? Considering that the penetration of electric vehicles is pretty low, okay? Then because the number of electric vehicles in New York City is pretty small, then even we change their charging behavior, it actually will not change a lot on the power grid or the power plant generation plan, okay? However, in Shanghai, it's totally different because nowadays we already have more than 2 million registered electric vehicles. It accounts for more than 30% of vehicles in stock. Then you can imagine, what if all the electric vehicles, they recharge their battery at the same time? It's going to be a big problem, okay? So it will definitely affect the power plant generation plan. And in Korea, I figured out that there is more than 3.7 million electric vehicles as of April of this year. Is also a big number, okay? So for these countries and cities, actually we have the need to consider the interaction between the EV charging behavior and the power plant operation. Okay? So we developed a modeling framework to quantify the value of ordering the electric vehicle charging on carbon emission reduction considering real work, electric vehicle users, travel and charging behaviors, as well as the interaction between the EV charging behavior and the power plant operation. We would like to fill the two gaps, okay? So in our study, actually we use a data set consists of 4,000 battery electric vehicles, okay, in Shanghai over 11 months. It actually, the data include the state of the charge, okay, the state of the charge of the battery, and also the mileage, the location, and the state, okay, whether the vehicle is traveling, is charging, or is parked, okay. We collect all those data. And also we have additional the 6,000 plug-in the hybrid electric vehicles. But in this study, we did not make use of this data. We only focus on the battery electric vehicle because for the plug-in hybrid electric vehicles, some of them may use gasoline instead of electricity. Okay, so we don't consider them. So the data comes from the Shanghai Electric Vehicle Public Data Collecting, Monitoring and Research Center, which we call Shanghai EV Data Center. It collects the data of all passenger and commercial electric vehicles sold and registered in Shanghai since 2015. Okay? Nowadays, it collects almost every vehicle, okay, every electric vehicles, okay, data in Shanghai, more than 2 billion. Okay, and covering 200 brands and more than 3.6 thousand vehicle types, including some local Chinese electric vehicle brands, as well as some companies from Korea, from United States or Europe. Okay, so the collecting frequency is 10 to 30 seconds. Okay, so it means what? It means, for example, I purchased the one electric vehicle 2 years ago, okay? And then after learning this, I noticed that actually I don't have any secret, okay? Because every 10 to 30 seconds, okay, actually the data, the center knows everything about my travel behavior, okay? When do you park? When do you charge? Okay, and how much do you charge? Okay, where are you living and where is your working location? They know everything, okay? But the good news is that because the data is quite sensitive, okay, it's not open to the public, okay? And yep. And the data, actually, we don't have even for us, we have a long-term collaboration with them. But we can only access, okay, trip data instead of the whole trajectory data set. Okay, how to define a trip data? Okay, for example, like this one. At the beginning of one event and at the end of one event, we have the data of these 2 points. Okay, for example, if a vehicle starts to drive at T0 and then stop driving at T1, okay, then we only have the data at T0 and T1, okay? We don't have the trajectory data between T0 and T1, okay? This is what we call the event or the trip data, okay? So then given this type of data, actually we can construct the travel trend of each electric vehicle. For example, this is one example, okay? The driver will start driving from T0 to T1 and then park, okay? Until T2, then the driver start to drive, okay? And park at T3. And then until T4, it start to recharge its battery, okay? And so on, okay? At each time step, we have the location data, we have the SOC data, okay? Then T3 and T6, it actually represents the time window when the electric vehicle is ready and available to be charged, okay? Do you know why? Because between T3 and T6, the vehicle is parked, right? It's not moving. And secondary, within this time window, from T4 to T5, okay, the vehicle conduct a charging behavior, right? It means, hey, we have a charger nearby, okay? And also the driver will have a motivation to recharge their vehicle, okay? This is the historical data, okay, right? So we identify T3 to T6, okay, as the charging time window, okay? So the time from the last driving event before a charging section to the first driving event after the charging section, okay? And that's why T3 and T to T6 is a charging time, is a charging window, okay? So T1, T2, unfortunately, this is not a charging window, okay? Because we cannot tell, okay, whether there is gonna be a charging facilities nearby. Because according to the historical data, this vehicle was not charging, okay, during this time window, okay. So then what we are gonna do, we are gonna change the charging behavior within the charging window, okay. As I mentioned, we have 11 months of data, okay, for each individual user, okay. Then it means for each traveler, we have many charging time windows, okay, in their travel chain. So our idea is that we just change the charging behavior within those charging windows and to see what's going to happen, okay? So this cannot be handled by the existing, the previous literature based on simulation. Simulation, it should be fine, but simulation is not real world data, okay? And by the survey, unfortunately, you cannot identify this one, okay? Maybe you can collect this data, this answer. However, you don't have the data for the driving distance, something like that. I'm gonna show you how we are gonna make use of the travel chain. And yeah, so I'm gonna show you some simple formulation. So EIJ is the remaining the energy in coordinated electric vehicle I before the J's charging event. So here, I define coordinated electric vehicle, okay? Because we believe that not all the electric vehicle users, they are willing to follow your guidance to change their charging behavior, right? It could be only a small portion of the electric vehicle users, they are willing to collaborate, to follow, to obey your recommendation, okay? So we define this set of electric vehicle as the coordinated electric vehicle, CEV, okay? So EIJ is the remaining energy, okay? So, and CIJ, okay, is the charging power for CEVI during the J's charging event in time interval R, okay? For charging window, actually we split it into multiple intervals, small intervals, okay? So we use R to indicate each interval, okay? Then actually this term represents, sorry, I cannot control it. This term actually represents the total energy recharge during the J's charging window, okay? Because delta here represents the duration of each time interval, okay? Charging power multiplied by the time interval is the energy, the recharge energy, okay? For that during that particular time window. And minus QIJ. QIJ is the electricity consumed by this particular electric vehicle between the J's and the J plus charging window, okay? The two sequential driving event, I would say. So we have this equation. So at the beginning of the trip, okay, so at the end of a driving trip, this is the remaining energy. And then plus the recharge electricity. Then and minus, okay, the energy I'm gonna consume for my next few trips, okay, before the next charging event, okay, then it's equivalent to the remaining electricity of the electric vehicle before the next charging event, okay. It's just energy conservation, okay. And then, of course, for QIJ, I would like to highlight, okay, it comes from the historical data, okay, based on the travel trend that we construct. And for the charging power, we need to guarantee it cannot be negative, because in Shanghai or in the whole China, we don't have the V2G technology, or the V2G technology is not that common yet, okay? So we don't consider a negative charging power. And this one is the maximum charging power is a parameter derived from each individual's historical charging data, okay? And this one, we want to guarantee at any time after charging, the remaining electricity should not be greater than the battery capacity, right? Or the maximum one, okay? This is the battery's capacity. You can understand it like that. And also, at any time, we need to guarantee the vehicle is not running out of energy, okay? So this minimum, it could be 20%. For me, I normally control the battery, the remaining energy to be greater than 20%. Otherwise, I can feel range anxiety, okay? So that's the constraints to guarantee the electric vehicle's charging profile can be satisfied, I would like to say, okay? Even because we want to change CIJ, okay? However, after changing this value, okay, we should guarantee each individual electric vehicle users, they can still finish their trip, okay? It means when I change their charging schedule, it will not affect their daily operation, okay? This is very important. And then we adopt a bi-level problem to formulate this problem, a bi-level framework. So in the upper level, okay, from the strategies evaluators' perspective, we would like to change the charging strategy of all the CEVs, the coordinated electric vehicle users. Okay, we want to change their charging schedule, okay? And then as a result, the aggregate electricity demand will be changed, will be affected, okay? The objective of the strategy evaluator is to minimize the total carbon emission, the carbon dioxide emission, okay? And in the lower level, because the aggregate electricity demand has been changed, okay? Then the electricity dispatch plan generated by or decided by the electricity utility corporation, okay, will be affected, okay? Once the plan is affected, then the electricity supply will be changed. And as a result, it will affect the upper level's decision, okay? And for the lower level, from the electricity utility corporation perspective, the goal is to minimize the total dispatch cost, okay? For example, in China, okay, this corporation actually, what they care is the profit. Of course, they also care the carbon emission, but that is not their major goal, okay? The major goal is to maximize the profit or equivalently minimize the total dispatch cost. Okay, as we can see, for these two levels, actually their objectives are not the same. They are not consistent, and that's why we adopt a bi-level problem to model it. Okay, so we use LT to represent the aggregate electricity demand at time step T okay, and we use GKT to represent the electricity supply from the KAIST plant at time step T. So then we first look at the low-level problem. The low-level problem aims to minimize the total power dispatch cost at each time interval, okay? And so the objective function can be represented by this one. MKT is the on-grid tariff for plant K to generate 1 unit of electricity during period T. I'm not sure in Korea, okay? But in China, this cost, this tariff is fixed, okay? It's controlled by the government, okay? In the United States, it's different. They adopt an option, okay, to determine this price, okay? But in China, it's given by the government or controlled by the government, okay? So it's a parameter here. And the first constraint is to guarantee, hey, the total supply, electricity supply, should be large enough to support the demand from, okay, LT, let me see. LT is the demand from the electricity, electric vehicles, okay, where I mentioned in the former slide, okay? And BT is the other electricity demand, for example, from the company, from the industry, okay? So we need to guarantee the total supply is greater than the total demand. And the second and the third constraint is to guarantee, hey, for the power plant, it cannot change the supply significantly, okay? For example, at time step T, okay, this is the supply, then unfortunately, you cannot increase the supply significantly at the next time step. There is a bound. There is a kind of upper bound and lower bound, okay? And this one is the capacity, okay? The generation capability of plant K, okay? It's determined by PK min and PK max, okay? These are also another two bounds. And subject to LT comes from the aggregated electric vehicles electricity demand. So this is the low-level problem, okay? We would like to minimize the dispatch cost. And for the upper-level problem, okay, the government wants to minimize the total carbon dioxide emission and how to measure this objective function, okay? We define FK, okay, as the carbon emission function, okay, of plant K. Then how to calculate it? It can be calibrated by a polynomial function like this one, okay? So A, B, C, for each plant K, there are parameters. We can fit them. We can calibrate these values based on the real-world data. And given the calibrated emission function Fk, actually, the upper-level problem is nothing special, but with an objective function like this one and subject to each individual electric vehicle's charging profile that I define, okay? That's the upper-level problem. The government wants to change or manipulate the charging schedule without affecting the driving behavior or the travel behavior of each individual electric vehicle, okay? And in a way to minimize the carbon emission, okay? So this is the bi-level problem, okay? The objective function is to minimize the total emission and and these constraints highlight rearranging the charging schedule while ensuring the travel needs of electric vehicles are met. And the low level is the power dispatch plan to minimize the total dispatch cost while satisfying the electricity demand, okay? The model is pretty simple, okay? But it's a bi-level problem, then it's not easy to solve. And then we apply sensitivity analysis method, and also we apply the parallel computing techniques to solve this problem efficiently. Okay, I'm gonna skip that one. And then I would like to show you the data and the results. These are the most important parts, okay, I would like to share with you guys. So the study, as mentioned before, utilized charging and driving data from about 4,000 battery electric vehicles, okay, in Shanghai, covering 11 months and including the 5 million driving records and 1.5 million charging records. This figure shows the charging profile of 3 electric vehicles, okay? And the right-hand side figure shows the aggregated electricity demand for all the battery electric vehicles that considered in this study. And regarding the power plant data, actually we collect the local generators in Shanghai, okay? They are public available. And we also, for example, the share of energy source in Shanghai's local plant, and also the list. Here is the list of thermal power generators in Shanghai. And also, we collect the data from the Shanghai's external power supply. Okay, for example, the Anhui East transmission project, and the Three Gorges and Gezhou Ba programs. Okay, we also collect their data, and then we need to calibrate the objective function of the upper level problem in the upper level problem. Okay, actually, based on the collected data, we can calibrate this function, the F function, for each plan. Okay, and it's a relationship between the carbon emission as well as the supply or the generation plan at that particular plant. And we also identify the minimum load and the ramp rate of each generator, okay, which is the upper and the lower bound that I mentioned. I highlight a little bit in the formulation, okay. And for the electricity demand, okay, outside of the electric vehicles, unfortunately, we don't have the public data, okay, because this is a sensitive information, so the government will never open it to the public. So, however, we find out some Shanghai hourly load curve and also the daily peak electricity demand curve, and we use some simple simulated techniques to generate, okay, the electricity that comes from the other activities, excluding the electric vehicles, okay? And then, at that moment, when we conduct this research, okay, we only have 380,000 battery electric vehicles at that moment, okay? Now they have more than 2 million, okay? So at that moment, our data set, it actually represents 1% of the whole electric vehicle fleet in Shanghai. It's not a small it's not a small portion, I would say, okay? Our finding, first, the carbon dioxide emission contributed by all battery electric vehicles is calculated as 1.1 million tons. You may not have a concept, right? So we convert it to 73 grams per kilometer, okay? Then you have a better understanding, okay? Without any regulation on their charging schedule, the carbon dioxide emission rate for one battery electric vehicle is 73 grams per kilometer, representing a 55% reduction compared to the conventional gasoline vehicles, which emit 170 grams carbon dioxide per kilometer. So it actually answers the first question, okay? Even without any regulation on their charging behavior, electric vehicles is much greener than the gasoline vehicle in terms of the carbon dioxide emission, okay? We show that. And the comparison, and after the optimization, okay, this figure shows the charging schedule before and after the optimization for 1 week period, okay? And the green, this green bar represents the charging window that we identify from the historical data, okay? And as we can see, the blue curve represents the original schedule, and the red curve represents the optimized one. As you may see, we changed it significantly, okay? They're not overlap, okay? For example, this one, actually we postponed the charging plan, okay, right? And for this one, we terminate the charging activity earlier than the original plan. Okay. By doing that, actually, this is the SOC of one vehicle over 1 week, as we can see. Significantly, we change the charging plan, the original charging plan. Okay. And this one is the cumulated charging amount. Okay, we change it significantly. So, and if we aggregate, okay, the charging demand for all the CVs, coordinated electric vehicles, we can see this one. Okay, this is the aggregate change, I would say. The blue one is the original one, and the red one is the optimized one. So, okay, not only for individual the electric vehicles, but also for the whole fleet. Okay, for the aggregated level, actually we change the plan, the charging plan significantly. Okay, and how's the performance? Okay, this figure shows. Okay, the blue bar represents the original emission. Okay, before the optimization, and after the optimization. Okay, oh sorry, this is the reduction. Okay, the green curve, the green bar represents the reduction. It's significantly, okay, especially in summer, because during the summer the emission is the highest, and accordingly the reduction is also the highest. Okay, and this figure shows, hey, what if we change the proportion of the electric vehicles, okay, from 1% to 100%, what's going to happen? Okay, nowadays, if we only control 1%, then what's the percentage of carbon emission reduction can be achieved? Okay, so look at this curve. It represents that this number is actually about 0.47%. Okay, it means if we control 1% of the electric vehicles' charging behavior, we can reduce the carbon dioxide emission by 0.47%. Okay, we control 1%, and then we can reduce about 0.5%. It's a significant large number, I would say. What if we control 100% of the electric vehicles? Suppose that all the electric vehicles in Shanghai should follow my order to recharge their batteries. Okay, we can reduce the carbon dioxide emission by 40%. Okay, so this is the information I would like to share with you guys. And then we conduct some sensitivity analysis, okay, to see, hey, what if we enlarge the battery size? What's going to happen? Apparently, if we enlarge the battery size, it means that we have more room to optimize. Okay, the constraint or the feasible set is going to be larger. Okay, if the feasible set is larger, then of course we can achieve a higher reduction. Okay, however, such an impact will become marginal as the battery increase by more than 50 kilowatt hour. Okay. So, yeah, it highlights that enlarging the battery size is a good strategy. However, when the battery size is large enough, further enlarging the battery size helps nothing. Okay, and this figure shows the multiplier of the ramp rate. The ramp rate is to measure how flexible the power plant can change its power generation plan. Okay, the more flexible, okay, the higher, the higher ramp rate. Okay, as we can say, the higher ramp rate or the power plant is more smart. Okay, then actually the carbon dioxide reduction from the charging regulation, charging behavior regulation or optimization, actually the impact will become more and more marginal. Okay, that's reasonable. Yeah, and we also further consider, hey, what if we have further install wind powers? Okay, then how it's going to affect the performance? And because I think we still have 5 minutes, right? So in the former introduction, I showed you guys, as long as we can guarantee the travel of each individual electric vehicle users is not affected, okay, then we can change their charging behavior, okay, to the level that we wish to control, okay. But in reality, we may not have the data, okay. For example, tomorrow, what's your activity? We don't have this type of data. Even for you guys, some of you may not know, hey, tomorrow, where I should go, right? So given that, what if the user just uncover the information to the system, to the government, hey, I want to charge this amount of electricity during this time window, okay? So we change this one, we fix this one, okay? The charging amount of electricity within a charging window is given, okay? If we fix this one, then what we can do is to change the charging time, okay? Yeah, for example, here. Now, you told me your electric vehicle must be recharged by 10 kilowatt hour between T3 to T6, okay? Then this is the number you want to highlight. Then the system, I'm going to satisfy your request, but I'm going to change the charging. For example, I may start the charging earlier than T3 or finish the charging later than T5, okay? That's what we can do, okay? By adding such a constraint, we can figure out that the restricted charging schedule, okay, can still achieve the 0.23% of the carbon emission reduction if we control 1% of the electric vehicles, okay? So here is the conclusion, okay, the findings, okay? I'm not gonna repeat it, okay, due to time limit, okay? And that's all for not today's presentation, but for the first topic's presentation. And yeah, thank you.